So my work that I'll be presenting is on data-driven and dynamically feasible trajectory generation for real-time power descent guidance and robotic exploration. And then a little bit about me, I'm Julia Bryden, a current PhD candidate at MIT and a NASA Space Technology Graduate Research Opportunities Fellow. And thank you again to my committee. So the overall topic of this dissertation is on trajectory generation, with the goal of being able to autonomously maneuver a vehicle from its current state to a desired goal location. And this goal location is denoted using targeting. So targeting is kind of selecting that goal location. And trajectory generation usually comes in 3 separate parts. So one of them is guidance, or determining the path to take from that initial condition to the desired goal state. And then after generating that trajectory, our control enables us to execute the planned trajectory and then control if there are any deviations in that plan. And potentially, your vehicle will veer so far away from that trajectory that it needs to be recomputed. And so guidance will need to take over again and recompute that planned trajectory after the deviation. And then the final component of this GNC architecture is navigation. So estimating the vehicle state and ensuring that reflects what we expect from our guidance solution. And this dissertation will specifically focus on trajectory generation as it relates to guidance, especially open loop guidance, or sometimes denoted as motion planning. So open loop means kind of generating this trajectory, while closed loop kind of refers to if you were to include the guidance and the control component. And to briefly give an overview of the state of the art of trajectory generation, specifically for power descent guidance, trajectory generation is usually achieved via a closed form polynomial spline. So for example, an equation that's kind of a function of time, and then in a long track and cross track set of coefficients, or a general set of coefficients, are determined ahead of time to compute these polynomial splines. And this is quite efficient because it's an explicit closed form solution. But some issues that sometimes happen is that these trajectories may not be minimum fuel trajectories, especially for long horizon times. And then also they don't directly incorporate state and control constraints, especially in a general formulation. So if we want to be able to incorporate generalized constraints on our state and control, so for example, the glide slope constraint shown in green, or maybe a pointing angle constraint shown in gray, then we want to use a direct optimization-based process. So this can be either maximizing our final mass or minimizing our fuel consumption, subject to a set of dynamic state and control constraints. And this is done using a numerical optimization solver. And this is done on board, or the goal of being performed on board. So that's why we have discretization nodes, because we need to have it in a discretized format to be able to solve for this optimal trajectory. So let's see what we're trying to run this on. So here's a list of different flight grade processors that have been used for some different missions. So for example, a free flyer, traditional class B, or a CubeSat. And what we're looking at for power descent guidance is specifically radiation hardened processors. So a good example of this is the RAD 750. And so if we compare the RAD 750 to alternative processors, so even a Raspberry Pi 4, it's significantly lower in performance, specifically millions of instructions per second, as well as clock speed, compared to even a Raspberry Pi. And we have a current NASA TABS requirement of efficiently computing large diverts, or these spacecraft guidance trajectories, in less than several seconds on a 100 megahertz class processor. So that's even lower performance compared to the RAD 750 in this description. And so a current problem that we're trying to address is that optimal control approaches, specifically using direct numerical optimization, are not computationally efficient enough to run on resource-constrained processors for long horizon problems. So this can be upwards of 20 discretization nodes. They start being on the level of seconds, and then after that, even on the level of minutes in terms of runtime. So how do we improve the computational efficiency of these direct optimization-based methods? Well, one option that makes intuitive sense is looking at the process of learning. So the way learning works is we can offload a lot of that computation and like time-heavy problem solving into a training phase that occurs offline instead of online. So we can use a process called backpropagation to train a set of weights and offload that computational complexity. That then, when we move into our online scenario or online inference, then we can perform a set of efficient matrix multiplications to efficiently inference either the solution for that problem or something that will reduce the problem size. And current methods have looked at both ends. So if we look at a spectrum between model-free reinforcement learning and numerical optimization, for model-free reinforcement learning, this is kind of on the opposite side where we don't really have a model, but we have an agent that's taking multiple actions in an environment, getting feedback from that environment on the reward that you're getting, as well as the next state that you're achieving. And you can kind of fine tune the policy that that agent is taking to make it as close to optimal as possible. And then on the other side, we have numerical optimization, which I would say is the like top of model-based methods. So you have a full model of your dynamics, state, and control constraints, and then a cost function. And you, for, I guess, specifically an interior point method or for a general QP solver, you often solve a Newton system to get a set of variables that describe your Newton step size. So kind of how big of a step you can take such that it's safe inside of your feasible region, and try to converge to that KKT point or your optimal solution. So for model-free RL, some examples of previous literature would be imitation learning. So an example of you want to learn or mimic the policy developed by model predictive control to drive a car, steering away from obstacles, as well as proximal policy optimization, which is another form of kind of reinforcement learning. Now on the other side with numerical optimization, we have G-fold or guidance for fuel optimal large diverts. So this was kind of one of the first usages of optimization on board. And it's kind of the beginning of lossless convexification and one of the only kind of optimal control algorithms that were used on board a flight test, at least, not on a mission. So now moving towards the middle, we do have specific applications of reinforcement learning or model-free RL as applied to trajectory optimization approaches. So specifically deep Q learning used for kind of reinforcement learning to enable autonomous aerobraking, as well as an application of PPO to Six-DOF power descent guidance trajectory generation. And then we have methods that are kind of closer to the middle. So for example, if we have a mixed integer convex program, but it's really difficult to get the values for our mixed integer variables, then we can actually use, for example, a convolutional neural network and predict what those kind of discrete variables will be, and then use that in the solution for our convex program, but still use that convex programming solver. And so this work presented today also falls in the middle of model-free RL and numerical optimization with the overall goal of leveraging machine learning to allow kind of the most efficient warm starts possible to a solver, while still maintaining the underlying guarantees of using that numerical optimization framework. And so most of the frameworks look a little something like this, where we have parameter inputs, and then leveraging a deep neural network, we're able to predict both an initial guess as well as tight constraints to guess the solution, and use that as our kind of initial guess in the numerical optimization section, but then also predict a set of tight constraints to formulate a reduced problem that we can then solve, and then use the solution of that to warm start the full problem to ensure feasibility and constraint satisfaction. But if you're already quite close to that optimal solution, then you're going to take only a few iterations of that full solve. And so that's the goal of today's work. And then specifically, we want to emphasize that we maintain the underlying guarantees of the solver through that last solve step. So some terminology that I will be talking about today and will come out throughout the presentation kind of mostly leverages convex optimization, where convex really means the cost function or your constraints satisfies this inequality that's defined with respect to the gradient of that function. So it's always lying above this line. It enables you to have some nice properties, including a globally optimal solution, a certificate of infeasibility, and then also polynomial runtime. And then second order cone programs are kind of a special case of convex and can include certain convex constraints. And then for a non-convex function, so as you see at the bottom, instead of having one global minima, you're going to have multiple local minima. And so you might still have a global one, but there's no real guarantees that you're going to converge to that global minimum. You'll likely converge to a local minima. And now this part is very important. It describes what a tight or active constraint is, and specifically when I mention it in this work. So if we look, we have a gradation that shows the direction of decreasing cost. So it goes down, and then we have a set of constraints that define our feasible region. And so the constraints that pass through the optimal point, and then if removed, would result in a decrease in the cost function. So we see that blue constraint and the red constraint. Those are what we call tight constraints. And specifically, if these are inequality constraints, then if they are active or tight, then they actually satisfy the equality of that constraint. So they then become equality constraints. And so that's why they're called tight. So now I'll give an overview of my PhD contributions, including my list of publications. And then I specifically have 3 separate topics in this dissertation. And they cover these 3 high-level problems. So one of them is if we can use neural networks to reduce trajectory generation time on space-grade hardware. The next question is how do we train these neural networks better? So specifically, we're looking at embedding constraint satisfaction into our loss function and seeing if we're able to bias towards constraint satisfaction when we do that. And the last one is what happens when we incorporate uncertainty. And so we're going to look at combining targeting and guidance by incorporating a risk-based landing contour. So for this first method, we're going to be addressing the problem of direct optimization-based guidance not being computationally efficient enough to run on resource-constrained processors. And the set of contributions for the section include the first transformer neural network architecture for power descent guidance trajectory generation. We also demonstrated this is a key technology for efficient trajectory generation through a series of benchmarking problems. And these benchmarking problems include 3 degree of freedom and 6 degree of freedom Mars power descent guidance, in addition to comparing to alternative interpolation and nearest neighbors based schemes. So going back to our basic optimal control problem, our goal is to minimize a cost function, so j of x, subject to a set of constraints, which we call C. And for the spacecraft guidance problem, this then becomes a semi-infinite optimization problem where we have a cost function that depends on time and is integrated over time. We also have a set of equations of motion, a set of inequality constraints that describe our state and control constraints typically, and then also a set of boundary conditions that ensure that our start and our goal locations are met. So often this problem for power descent guidance is non-convex, but there's a well-known process of lossless convexification that enables globally optimal convergence to a solution. So it turns that non-convex problem into a convex problem that has a global minimum. And this is through introducing a slack variable that's in replacing thrust, and then also including a Taylor series expansion. But what we care about is how big is this problem? What are we trying to solve? And so the first thing we can do is count up the total number of constraints. So n is our number of discretization nodes. And if we count them up, we have 15n plus 9 total constraints. And so if we see, as we scale our number of discretization nodes, our number of constraints can grow quite rapidly because it's quite a high function in terms of being linear. So we see over 100 discretization nodes, we're at already over 1,000 constraints. And the green line shows if we only had the equality constraints, what is the lower bound of what we could achieve if we were able to minimize the number of inequality constraints that we don't need. So what do I mean by that? Let's take a look at a really basic problem that we've seen previously, where we have a feasible region and we're employing, for example, an interior point method where we have this system of equations that we're iteratively solving. And the size of the system of equations depends on the total number of constraints, which we reviewed previously is quite high. But we can start at a point in the feasible region and iterate until we find that optimal point at the bottom. But what if we knew the set of tight constraints, which are the only constraints that matter in terms of defining that optimal solution? And if we can identify the set of tight constraints, then we can both significantly reduce the size of the system of equations we have to iteratively solve, as well as take a more direct path to our optimal solution. And that's exactly what we plan to do. So specifically, we're looking at both tight constraint and final time prediction. So learning and mapping from a set of parameters to something we denote as a strategy. So that's our set of tight constraints and optimal final time. And our parameters for a 3 degree of freedom power descent guidance landing case include our initial state, so initial velocity and initial position, as well as parameters defining our constraints, so glide slope angle, pointing angle, and engine angle. And then our strategy is now a binary vector that depends on the number of discretization nodes that our problem is defined with. And so this binary vector at each node indicates either a 0 if a constraint's not tight or a 1 if the constraint is tight. And then we're also predicting the floating point final time, which is scalar, because otherwise we would have to perform a line search over possible final times, and that significantly increases your computational complexity. So there's a few different ways that we could learn or estimate this mapping to achieve our set of tight constraints and final time. Since this is likely very nonlinear, it makes sense to employ a learning-based method. There's been previous approaches of kind of applying optimal classification trees or feed-forward neural networks to learn warm starts. But often, if your problem is highly time-dependent, then they end up not working as well. But then compared to RNNs and LSTMs that were previously used for a lot of time-dependent prediction, transformers have been shown recently to perform quite well in terms of efficiency during training time. So they work really well in parallel, and also directly learning relationships between parts of your sequence data. So our input is not a sequence, but our output is a sequence, and so that's why it's important. And so here's the overall architecture for transformer-based power descent guidance, or T-PDG. So we have our set of parameters that are time independent 9x1, and then we encode them, have a positional encoding, and then the transformer encoder is kind of the most important component, and it includes the attention and cross-attention layers. And then we decode it down to that set of tight constraints and optimal final time, where the tight constraints is determined by our number of discretization nodes, or N. And then for the architectures for T-PDG, so constraint prediction is kind of a larger number of dimensions because we're predicting something that's time dependent, while for final time, it's quite small because we're just predicting that scalar value. And then something to note for this architecture is that the inference time is very efficient, so 2 to 3 milliseconds. So compared to other potential warm starting techniques, it will beat it out in terms of prediction time as well. So now looking at the training and test process. So often practitioners will already have the data for this training process shown in step 1. Because often they will have a set of Monte Carlo samples that they've done either for their mission design or for contingency scenarios. And so you can just take that data set and test where the constraints are tight and then feed that right into the training phase. But in our case, we didn't have that. So we used a simple uniform sphere sampling around trajectory, iteratively chose our initial conditions, or theta, solved with ECOS, which is an SOCP solver, and then get our set of tight constraints, optimal final time, and then take that whole data set into part 2 and separate it into training and test data so that we can train the mapping, but then also ensure that our test data is not overlapping with our training. And then finally, for our real-time application, we want to see the performance of this method end to end. And so we now took our test data, fed it into our neural network mapping to get an inference of what are the tight constraints, what are the final time, formulate a reduced problem that's only the size of those constraints we predict to be tight, solve it with the optimal final time, and then use that as an initial guess to the full problem, which we call our feasibility test, to ensure that all constraints will be satisfied, even though we're using a learning-based approach. So here are some of the test time trajectories plotted out. And specifically, we want to go over an application that's 3 degrees of freedom, T-PDG. So we're testing for 50 discretization nodes. And then we took a little over 240,000 samples divided into training and test data. And then we want to compare against the benchmark time of LCVX, or lossless convexification. And that one took about 1.6 to 1.7 seconds in terms of solve time. And so when we compare with T-PDG, we get the following timing results. So specifically, we were able to reduce the mean computation time of LCVX by 78% when we applied T-PDG. And specifically, we got a mean computation time of 373 milliseconds, and even within 1 standard deviation. So as you see on the right side plot, we're still under the 1 to 2 second requirement as demonstrated by NASA. And then also the use of a feasibility check ensures that we have 100% feasibility, even though we're using a learning-based approach. And then all the way on the right, you can see the timing results for each portion of T-PDG. So if you wanted to see how long the neural network prediction compared to the reduced solve, comparing to the feasibility check, you see that both the reduced solve and the neural network prediction are quite small and have quite a low standard deviation in terms of solve time. So now that we tested T-PDG in 3 degrees of freedom, an even harder problem to test on is extending to 6 degrees of freedom. So while before we were treating our spacecraft as a point mass, Now we're actually considering rotation. So we have a quaternion that denotes kind of what rotation our vehicle is in, and then also angular velocity to get the velocity of that rotation. And we also include lift and drag in this formulation, specifically for a Mars power descent guidance problem. And to solve the Six-DOF problem, it's different from lossless convexification because now we have non-convex state constraints that can no longer be losslessly convexified. So then typically a successive convexification algorithm is used. So instead of just solving one problem, we're now solving a successive set of convex optimal control problems. And so while each one of these problems have a global minima, you might still converge to a local optima, and that's kind of the reality of non-convex optimization. And the overall way that this works is we have an accepted iteration or a rejected iteration at each point of our iterations. And then we have a trust region, which is kind of how far out we trust our convexified problem. And so an example of this would be we started kind of inside of our bounds, and then after one iteration, we found that we actually have a greater actual cost change over our predicted or linearized cost change. And so we decided to grow our trust region. And then we see that we're getting pushed towards the constraint boundary, and that's kind of induced by an addition of a virtual control variable. And then if we're between our actual cost change divided by our linearized cost change is between our two parameters, then we're not going to grow or shrink our trust region. And then if we end up at a point where actual cost change over predicted cost is less than a parameter, then we'll continue shrinking our trust region. And this all continues until we converge to an optimal solution. And an example of this process is shown here by Mao, where we have kind of our change in J, which is our non-convex cost over our convex cost L. And we see it kind of iterates up and down until we actually converge to our final solution. So for applying T-PDG, or now denoted TSCBX, to the Six-DOF problem, we now have a larger set of both parameters and strategy vectors. So our parameter list now includes our quaternion and angular velocity. And then our strategy includes kind of the Six-DOF constraints now, still a binary vector. But now something to note is compared to the convex problem, this non-convex optimization problem is quite sensitive to your initial guess. And so instead of only predicting the final time, the optimal final time, it makes sense to use this transformer framework to also predict your entire trajectory as well as optimal control input. So that's our X star and our U star. And something to note here, so we know with T-PDG previously, there was quite a lot of samples used. So in this case, we wanted to see kind of how low we can go on the number of samples while still maintaining generalizability. And so in this case, we actually sampled less than 1,600 samples, but we rotated these samples every 45 degrees to get over 11,600 samples. Since we want to embed rotation and variance into our trained policy for the neural network. And so this allowed us to do that. Now to quickly, so this is what we saw before, but now explains the changes that were done to the algorithm specifically to allow for transformer-based successive convexification, since now we have a series of convex subproblems. So the first step happens with the initial guess neural network, where we predict our full solution trajectory and optimal control policy, as well as final time, and use that as an initial guess for SCVX. And then from there, we solve a reduced convex optimal control problem at every iteration using the predicted set of tight constraints for that iteration. denoted by the tight constraints prediction neural network. And note that this is still predicting the tight constraints only for the convex subproblems and not for the non-convex constraints that we're using in our cost function. So then when we compute the actual over the predicted linear change in penalized cost, then the only change we have is in the denominator. The numerator doesn't change. So we still require all constraints to be satisfied in order to converge to our optimal solution. So it's kind of the actual cost change. And so that happens when our actual cost change is equal to 0. So now for some timing results from TSCVX compared to SCVX. So we included tight constraint prediction as well as full solution prediction using transformer neural networks. Our mean solve time of almost 15 seconds for SCVX was now reduced by, or I guess improved by 66%. And was reduced to less than 5 seconds for TSCVX for the non-convex problem. We also applied this to, or like specifically applied this to Mars 6 degree of freedom power descent guidance to get these results. And then the GIF shows the series of kind of convex problems that converge to our optimal solution that corresponds to SCVX. So we showed that this works for both 3 degree of freedom and 6 degrees of freedom. But a reasonable question to ask is how this actually compares to interpolation and nearest neighbor-based strategies, because these might be a little bit more explainable or interpretable when compared to T-PDG. And so in this work, we did a benchmarking against 2 different approaches. So one of them is linear interpolation, and this method has been shown or been used previously in literature to speed up power descent guidance problems. So specifically using a table lookup method to efficiently interpolate between pre-computed trajectories as well as final time predictions. And in our case, we're benchmarking the linear interpolation that uses Delaunay triangulation for both tight constraint and solution prediction because we wanted to have a one-to-one comparison. And then the other method that we compared against was the KD tree. So this one's novel in terms of power descent guidance literature. Typically, it's been used in kind of like LiDAR point cloud clustering as well as ray tracing, but it works quite similar to branch and bound, where you have kind of a set of k-dimensional points, and you have a tree that compares each dimension. And then kind of crosses out the dimensions or the subtrees that are not as close as the closest point that you found so far. And so we perform the benchmarking in a similar way to linear interpolation directly against the tight constraint and the final time predictions. So if we look at our memory usage versus inference time, we have on our x-axis our inference time, and then on our y-axis memory usage. And then note that this is log scale, so they're actually quite different in terms of like memory and inference times. But we've also kind of like put on this plot static versus dynamic memory allocation. And from the green region, we can see that T-PDG is the only algorithm which consistently falls inside of the runtime and memory requirements for onboard usage. So specifically, when we denoted our memory requirement, we did it based on a RAD 750 SpaceWire estimate for SRAM. And then specifically using T-PDG, when compared to linear interpolation, reduces inference time by over 98%, and also lowers peak memory usage by 93%. So it is significant gains, especially compared to linear interpolation. So since this is a learning-based method, something of interest is looking into interpretability and generalizability. Specifically with the transformer encoder, we can provide a sense of interpretability and explainability by looking at dimensionality reduction techniques for that high dimensional embedding space. And so first we can consider explicit model predictive control, where our state space is divided into polytopes, each one denoting a different control policy. And if we apply t-distributed stochastic neighbor embeddings, it works in a similar way, where we're able to transform our high dimensional weights down into, for example, 2 dimensions that often fall into a set of clusters. So for example, I have 3 different clusters here, and each one denotes a sort of policy or classification for that deep learning method. So this is what our constraints transformer TSNE projection looks like. We can see that the number of tight constraints, so warmer is a larger number or larger total number of tight constraints, and then cooler is less tight constraints. And so we see that there's kind of 2 lobes that are forming. One of them has less tight constraints overall, and the other one has more tight constraints, or in general, a larger variation in the total number of active constraints. And if we use k-means clustering, then we can actually see kind of what points correspond to these low dimensional clusters. So map to our accuracy, for example. So we have cluster 1 and cluster 2. And if we actually look at our accuracy, the points that have less than 90% accuracy almost exclusively fall in that cluster 1, which, if we remember, is the cluster that has more tight constraints. So this is quite interesting. And a practitioner might want to know, well, if most of the inaccurate samples kind of reside in cluster 1, then what are the types of inputs or the distribution of inputs that lead to each cluster in the embedding space? And we can actually map back to get what the inputs are that correspond to each cluster. So this is an example for our Z position inputs, but all of the distributions look quite similar for each of our parameters. And so if we look at our Z position inputs and the distribution of each cluster, we see that cluster 2, which had more uniform, less number of tight constraints, has a quite small standard deviation and a mean quite close to the original trajectory that we sampled around when we did our uniform sphere sampling. While cluster 1, which had a lot more of the inaccurate points and also corresponded to the cluster that had a lot of tight constraints, has a lot wider of a standard deviation and a lot of points outside of that first cluster. And so what we can take away from this is that our cluster 2 denotes a sort of in distribution distribution. So samples, or if you have a set of parameters that are in this part of the distribution, then you're likely going to have an easier time classifying them versus out of distribution, where if we're quite far on the outside of that cluster 1, then we might not trust our neural network prediction as much as we would have in the green region. And so in conclusion, we were able to leverage the attention mechanism of transformer neural networks to enable millisecond level prediction of optimal strategies, lowering the average runtime for 3 degrees of freedom from 1.5 seconds to under 500 milliseconds, the Six-DOF from over 14 seconds to under 5 seconds, as well as benchmarking against alternative interpolation and nearest neighbor-based approaches, showing that T-PDG is the only memory and computationally efficient method when benchmarked. And then we also use TSNE to get a little bit of explainability on how our embedding space is classifying each of our samples, including which samples are denoted in distribution or out of distribution by the network. And furthermore, T-PDG is generalizable, so it can be applied to any optimization problem in which a feasible solution exists. So now that we went through the T-PDG process, a question that comes about relates to current deep learning-based methods not really being optimized for constrained optimization problems. So for example, they often prioritize cost minimization over constraint satisfaction. But for safety critical applications, we really care about constraint satisfaction. So how do we train these neural networks better? Well, in this next set of slides, we will go through the contributions of developing a set of Lagrangian-based merit functions that can be used in our loss while training, as well as showing that we're able to bias towards constraint satisfaction, benchmarking using both the LSTM and a feed-forward architecture applied to Lunar rover model predictive control. And then finally, demonstrating improved constraint satisfaction when compared to other methods in the literature. So first we can consider a quite simple optimization problem. So we have predict x subject to x less than or equal to 2. And if we guess, okay, maybe x equals -3, maybe x equals 3, what is our mean squared error for this? And if we're using this as a way to evaluate our loss for training, is this reasonable for a constrained optimization problem? So we see that x equals 3 has this quite a bit lower mean squared error compared to x equals -3 if we're trying to get a true value of 1. But if we actually consider a constraint, so that green region of x less than or equal to 2, we might actually prioritize x equals -3 because it's constraint satisfying instead of x equals 3, which is not constraint satisfying. And so the question becomes, well, how do we encode constraint satisfaction while we're learning? So if we consider our simple optimization problem again, minimize f of x subject to our inequality constraints, then a merit function in this case is defined as a scalar valued function that balances cost minimization with constraint satisfaction. The Lagrangian is a natural merit function. So we see our f of x, our cost, is added to lambda, our dual multipliers, multiplied by g of x, our set of constraints. And so we plan to leverage the Lagrangian to improve constraint satisfaction while learning. And so we introduce toast, or trajectory optimization with merit function warm starts, that utilizes this set of task relevant merit functions. And specifically, we're comparing to mean squared error loss. So we have mean squared error as well as primal mean squared error, which just means we're not predicting our dual multipliers. We now have introduced a Lagrangian-based loss function. So now we have the Lagrangians with their cost to constraint satisfaction balancing. We also introduced a Lagrangian with gradient loss function. So we also, if the gradient is 0, then we're at our optimal solution. And so we can add that as a kind of bias with that gradient. And then finally, Lagrangian mean squared error. So if you wanted mean squared error, but you wanted more of a slight bias towards constraint satisfaction, then you can add in that Lagrangian loss to your mean squared error, and that creates a bias towards the constraint satisfaction. And this is kind of inspired by our dual function. So if we have an x-axis that's constraint satisfaction, or g of x, and then our y-axis that's f of x, then the hyperplane is actually our Lagrangian. And the specific problem that we're looking at is lunar rover motion planning, which currently, especially in space-based robotic missions, are heavily based on search-based planners, which kind of similar to the polynomial power descent guidance methods, often disregard high fidelity dynamics, state, and actuator constraints. So what we really want to run on board is model predictive control. So being able to solve the planning problem subject to system dynamics and state and control constraints. And so here is the specific problem that we're solving in our benchmarking cases. So we have a simple bicycle kinematics model. And then our optimization problem is minimizing over jerk and acceleration, subject to our dynamics, some bounds on our state and control, as well as a set of obstacles. And we want to address this problem of MPC not being computationally efficient enough to run on flight-grade processors. And our proposed solution varies a little bit from T-PDG, where in this case, we're directly learning the time-varying policy and the dual multipliers using our neural network mapping. But specifically, this mapping is trained with task-relevant Lagrangian-based loss functions that I showed previously. And so if we look at the cost versus constraint satisfaction, so this is similar to the dual plot that I showed earlier, where we have our constraint satisfaction on the x-axis, our cost difference between optimal cost and predicted cost on the y-axis. And then the red region shows constraints that are, or like there's constraints that are not satisfied, and then green and to the left includes satisfied constraints. But kind of the optimal point lies at the bottom of that green line. And specifically, we can look at mean squared error and primal mean squared error and see that both of them are very much not constraint satisfying. Whereas when we use the Lagrangian, or especially Lagrangian mean squared error, we're quite close against that utopia point and that green line that includes constraint satisfaction. And then further, we benchmarked against a previous machine learning-based approach for relative orbit transfer that directly altered the architecture instead of the loss function. They altered kind of the last layer in that architecture to try to embed constraint satisfaction, but they actually noted that the average number of collisions increased when they did this. But then when we applied toast, we actually saw an increase in constraint satisfaction. So specifically by up to 5.33% for our LSTM neural network when compared to mean squared error loss. And then for some timing benchmarks compared to our full SQP or a sequential quadratic program in orange, we see that primal mean squared error and Lagrangian mean squared error are quite similar in terms of mean computation time. So both are about 3 seconds. Specifically, when applying these task-relevant merit functions, we saw reductions in mean runtime when compared to the SQP by up to 63%. And then when benchmarking against the previous work in literature on relative orbit transfer, we're able to show similar gains in terms of runtime reduction, down 3 or 4 second runtimes. And that's with using less samples than they originally used in their work. So in conclusion, we were able to generate a set of merit functions that balance both cost optimality and constraint satisfaction when we're learning for constrained optimization problems. Further, we were able to employ offline supervision and then online inference using these decision-focused merit functions and show that this overall architecture included a bias towards constraint satisfaction and also over a 5-second speedup compared to our original problem. Furthermore, we also saw that when we regularized mean squared error loss with the Lagrangian, we also improved the decision variable prediction accuracy in addition to constraint satisfaction, specifically in the LSTM neural network case. And so now we're going to move kind of further back and look at what happens when we incorporate uncertainty, and specifically looking at the problem of pinpoint landing when we want to determine a target autonomously and then compute a minimum fuel trajectory to that target location. And so in this work, we developed a novel algorithm for autonomously computing a probabilistic map for landing site risk, and then selecting that minimum risk landing site given a navigation image. And then we tested this using a lunar landing study benchmark that compares minimum risk targeting and includes direct optimization for trajectory generation. And so the full algorithm for this work looks like this, where we have a set of navigation imagery, which in this case we can detect craters, but in general we could detect different polynomial described shapes that we can use as obstacles. After that, if it can be represented as a polynomial, then we can determine a set of obstacles defined in this polynomial format. And then finally, generate a set of risk contours that over that discretized set of risk contours, we can find where exists the minimum risk landing location and find that autonomously just from an image. And specifically, we plugged this targeting algorithm into 3 degree of freedom power descent guidance, specifically lossless convexification, and then solve that optimization problem. So looking at the obstacle generation, so this is an example generation of kind of a set of obstacles that could exist, where we have a polynomial that describes each obstacle. And what's important about this polynomial is that we have uncertain major and minor axes, so that omega-1 and that omega-2, which could be either distortions in your picture, or it could be just like the pixels, you might be quite far back and the pixels are limiting, and so you have uncertainty associated with the actual size of that obstacle, which you can denote by a probability distribution. So now to compute the risk contours, we first want to define risk, which is the probability of collision with uncertain obstacles in the environment. And so the risk contour is described as a set such that the probability that the point that you're looking at is inside of one of the obstacles is less than or equal to an allowable risk percentage. So it's delta. So for example, if you want like 90% guarantee, then you have delta 0.1. And then you can redefine this probability distribution based on the polynomial that describes each of your obstacles. And so you want the probability that polynomial is greater than or equal to 0, less than or equal to your allowable risk. So now to actually compute this in a closed form, you have to perform an inner approximation using method of moments. And based on that inner approximation, you're just like a little bit more conservative with that allowable risk, but you're able to compute kind of in closed form what each of these values would be related to risk. And specifically, if you compute this for one obstacle, then you can combine them together by adding them for multiple obstacles. And so, for example, this is a very basic risk contour where if we just have two obstacles, then we can denote the landing target as the point of minimum risk. So now looking at a lunar power descent guidance problem shown here, where our goal is to land on the lunar south pole, and then using lossless convexification as our algorithm, assuming perfect control. Then we can then compute based on our example kind of landing site set of craters, compute the risk contours, and then choose the minimum risk landing location. But also, if you wanted to see all landing locations of a certain risk level, you could also kind of filter that out and choose a different landing location that fits your risk, your desired risk level. So this allows for automated obstacle generation, targeting, and then power descent guidance. So in summary, we were able to develop an improved computationally efficient trajectory generation algorithm for long horizon problems through 3 different warm starting frameworks. So one of them is T-PDG, transformer-based power descent guidance. Another one, TOAST, for trajectory optimization with merit function warm starts. And then finally, transformer-based successive convexification for 6 degrees of freedom. And then an additional contribution of combining targeting and guidance for minimum risk landing site generation. We also demonstrated each of these algorithms on a variety of representative problems. So both 3 degree of freedom and 6 degree of freedom Mars power descent guidance, 3 degree of freedom lunar power descent guidance, as well as a lunar rover model predictive control problem. We also utilized TS&E visualization methods to understand the policies learned by training these deep neural networks and provide insights into what is in distribution and what is out of distribution. And these developments offer a set of time and memory efficient algorithms to enable full-scale autonomy for both future power descent as well as robotics-based exploration. And then for our future work, potential options would be looking at multitask or active learning. So for example, training the constraint and final time neural networks together, or iteratively adding complex samples to improve model robustness and generalization. There's also potential for extended application, so applying T-PDG and TSCVX to ascent, abort, or other non-convex optimization problems. For successive convexification, something really interesting would be looking at tight constraint prediction to better warm start and provide convergence guarantees. So for example, developing trust region designs that use transformer generated predictions, or specifically, if you can predict the set of tight constraints, you could better promote sparsity in those matrix operations to improve efficiency as well. For toast, we're interested in looking at the Lagrangian-based merit functions in adversarial settings. For integrated power descent targeting and guidance, we could include different distributions for the uncertain parameters in our obstacles, as well as different obstacles like rocks or uneven terrain. And then finally, for flight and hardware verification, kind of the next step post-sim is to actually see how well these deep learning-based methods perform on flight-grade processors and in additional kind of flight-based scenarios. And thank you all. Thank you especially to my committee